Electromotive force, commonly abbreviated as EMF, is the voltage developed by any source of electrical energy. EMF is typically measured in volts and represents the electrical potential difference that drives current within a circuit. It's essential to distinguish electromotive force from electromagnetic force, as they are distinct concepts within physics. Electromotive force refers to the potential difference created by a source such as a battery or generator that can drive current around a circuit. It's the energy per unit charge available to move electrons through a circuit. The term force in electromotive force is somewhat misleading because EMF is actually a measure of energy per unit charge, not a true force in the mechanical sense. True forces are measured in newtons, while EMF is measured in volts, which are equivalent to joules per coulomb. Electromotive force is crucial for understanding how electrical circuits function. Without an EMF source, there would be no voltage difference to drive current flow. Common sources of EMF include batteries, which convert chemical energy into electrical energy, generators, which convert mechanical energy into electrical energy, and solar cells, which convert light energy into electrical energy. When analyzing circuits, it's important to consider the EMF of the voltage source as well as the internal resistance of the source. The internal resistance causes a voltage drop within the source itself, reducing the available voltage at the terminals. The voltage at the terminals is often referred to as the terminal voltage and is equal to the EMF minus the voltage drop across the internal resistance. Understanding the concept of electromotive force is foundational for studying more advanced topics in electrical engineering and physics, such as circuit analysis, electromagnetic induction, and power generation. Electromotive force plays a crucial role in Faraday's law of induction, which states that a changing magnetic field induces an electromotive force in a circuit. This principle is used in generators to convert mechanical energy into electrical energy. The magnitude of the induced EMF is proportional to the rate of change of the magnetic flux through the circuit. Electromotive force is also important in thermoelectric devices, which convert temperature differences into electrical energy. The Seebeck effect describes the phenomenon where a temperature difference between two dissimilar electrical conductors or semiconductors creates a voltage difference between them. This voltage difference is an electromotive force that can drive current in a circuit. In summary, electromotive force is the voltage developed by a source of electrical energy. It's essential for driving current in electrical circuits and is measured in volts. Electromotive force should not be confused with electromagnetic force. Electromotive force is critical for understanding circuit behavior, electromagnetic induction, and thermoelectric effects. When analyzing electrical circuits, the concept of electromotive force is central to understanding how energy is transferred and utilized. Electromotive force sources provide the necessary voltage to drive current through the circuit components, enabling them to perform their intended functions. For example, in a simple circuit with a battery and a resistor, the battery provides the electromotive force that pushes electrons through the resistor, causing it to dissipate energy in the form of heat. The amount of current that flows through the resistor is determined by Ohm's law, which states that the current is equal to the voltage, or electromotive force, divided by the resistance. Electromotive force is not limited to simple circuits. It is also relevant in more complex systems, such as power grids and electronic devices. In a power grid, generators produce electromotive force to supply electricity to homes and businesses. The electromotive force is carefully controlled to maintain a stable voltage level throughout the grid. In electronic devices, electromotive force is used to power the various components, such as microprocessors, memory chips, and displays. The electromotive force is typically provided by a battery or a power supply that converts alternating current from the wall outlet into direct current. The understanding of electromotive force extends beyond the theoretical realm and has practical applications in various fields. For example, engineers use electromotive force principles to design and optimize electrical circuits, ensuring that they operate efficiently and reliably. Technicians use electromotive force measurements to troubleshoot electrical problems, identifying faulty components and restoring circuits to proper working order. Researchers explore new materials and devices that can generate electromotive force more efficiently, leading to advancements in renewable energy technologies and energy storage systems. In education, electromotive force is a fundamental concept that is taught in introductory physics and electrical engineering courses. Students learn about the definition of electromotive force, its relationship to voltage and current, and its applications in various electrical systems. Hands-on experiments and simulations help students visualize and understand the concept of electromotive force more effectively. Electromotive force is a key concept in understanding the behavior of electrical circuits and systems. It represents the driving force behind the flow of electric current and is essential for the operation of countless devices and technologies. Electromotive force is the voltage developed by any source of electrical energy that drives current around a circuit.